In the winter of 1915, Einstein's field equations unfurled a new map of reality. Hidden within their geometry lay a prediction so extreme it felt almost absurd. The possibility of regions where gravity tightened into an inescapable knot, where space and time themselves could no longer return. A few months later, Karl Schwarzschild, writing from the front lines of war, provided the exact solution. He described a horizon of no return, a silent edge beyond which the fabric of the cosmos folded inward. For decades, it was treated as nothing more than mathematics, a curiosity without substance. Many physicists doubted that nature could ever produce such monstrosities, yet the universe had already written them into its story. By the 1960s, radio telescopes uncovered quasars, brilliant beacons powered by unseen engines. In the 1970s, Cygnus X1 revealed a star orbiting a dark companion, vanishing matter feeding something invisible and immense. Slowly, reluctantly, theory gave way to reality. New instruments followed, tuned to X-rays, radio waves, and distant whispers of light. With every improvement, the invisible grew clearer. Then came the triumph of the Event Horizon Telescope, a planet-sized array stitching together Earth's eyes to glimpse the unseeable. In 2019, it unveiled the shadow of M87 Manal, a ring of light bent by gravity's grip. In 2022, it resolved Sagittarius A's, the black hole at the heart of the Milky Way. But woven into the celebration were shadows of doubt, flares brighter than predictions, distortions that strained Einstein's equations, irregularities in the photon rings. Within the streams of data, anomalies stirred. They were subtle, fleeting, easy to dismiss. Yet they hinted that the horizon was not silent, and that the story of black holes was only beginning. In the winter of 1915, as Europe was consumed by the chaos of war, a quiet revolution in thought was unfolding in the mind of a single man. Albert Einstein, carrying the weight of exhaustion, fear, and relentless genius, unveiled his general theory of relativity. It was a theory so daring that it bent not only mathematics, but the very imagination of the human mind. Spacetime, he revealed, was not a static stage upon which matter performed. It was pliable, curved, alive, shaped by the gravity of stars, planets, and everything that exists. In this new vision of reality, mass told space how to curve, and space told mass how to move. Among the earliest to explore the equations was a German physicist named Karl Schwarzschild. Serving on the Eastern Front during the First World War, he worked under the shadow of illness and artillery fire, yet his mind wandered to the deep mathematics of Einstein's revelation. In a matter of weeks, Schwarzschild derived a solution that stunned even Einstein. His calculations described an object so dense, so compressed, that space and time themselves curved infinitely around it. At a certain radius, later called the Schwarzschild radius, nothing, no matter, no light, no signal could ever escape. Beyond this invisible surface lay a place where the laws of physics dissolved into silence. This radius was the event horizon, a term that would not yet be spoken, but a frontier already whispered into existence. At the time, the idea was regarded as an abstract curiosity, a mathematical phantom, rather than a prediction of something nature might actually permit. To imagine a star collapsing so completely that its very escape was sealed off seemed impossible, almost absurd. The equations allowed it, but the imagination resisted it. Even Einstein himself doubted that nature would be so unkind. For decades, black holes lived in the shadows of theoretical speculation, tucked into the margins of textbooks, regarded as extreme and perhaps irrelevant. The tide began to shift in the mid-20th century. Astronomers turned their instruments to the skies, and the heavens answered with mysteries too luminous to ignore. In the 1960s, radio astronomers detected strange signals, immensely powerful radio emissions pouring out of the distant universe. These became known as quasars, or quasi-stellar radio sources. To the eye, they looked like faint stars, but their light carried more energy than entire galaxies. Something unseen and unfathomably violent was releasing torrents of radiation across the cosmos. Theories converged on a startling conclusion. Quasars were powered by the engines of supermassive black holes, millions or billions of times the mass of the Sun. For the first time, the black hole was no longer dismissed as a mathematical oddity. It was promoted to the role of cosmic architect, the hidden furnace of galaxies themselves. Yet the evidence was still indirect. A quasar could be explained only through inference, through the dance of mathematics against the canvas of observation. Scientists crave something closer, something in our galactic neighborhood. In the 1970s, that wish was granted. The X-ray observatory Uhuru revealed a source in the constellation of Cygnus, a binary system where one star circled something invisible. The visible star shed matter into the void, and as the gas spiraled inward, it blazed with X-rays before disappearing entirely. Cygnus X1 was its name, and it became the first strong candidate for a stellar mass black hole. What had once been theory was now tightening its grip on reality. With every decade, the instruments grew sharper. Radio telescopes swept the sky, infrared detectors peered through dust, X-ray eyes pierced the high-energy domains of space. And slowly, the invisible veil around black holes began to reveal its outline. Astronomers noticed stars near the center of our own Milky Way moving with furious speed, as though they orbited a monster hidden in the dark. Their orbits traced a mass 4 million times the Sun, crammed into a region no larger than our solar system. Sagittarius A, the black hole at the heart of our galaxy, was there, concealed but undeniable. Still, no telescope could look directly into the abyss. The event horizon itself remained unseeable, a mathematical horizon beyond which all signals vanished. For nearly a century, humanity gazed at shadows cast by black holes, never at the thing itself. Then came an audacious idea: to build a telescope the size of Earth, not by constructing something impossible, but by linking existing radio observatories across continents into a single synchronized eye. The Event Horizon Telescope was born, a global collaboration of scientists, engineers, and visionaries, united across time zones and languages, pointing their instruments at the sky, synchronizing with the precision of atomic clocks, and capturing waves of light so faint they barely brushed against existence. In 2019, their work unveiled the unthinkable. A blurry, glowing ring appeared on the world's screens, the shadow of M87 HAO, a supermassive black hole 55 million light-years away. Its event horizon, once only an equation in Schwarzschild's wartime notebook, now stood in the eyes of humanity. 3 years later, they captured Sagittarius A, the heart of our own Milky Way. For the first time in history, humans had looked directly into the abyss, and the abyss had revealed its edge. It was a triumph celebrated as one of the greatest images of science, a confirmation of Einstein's vision painted in light and shadow. But hidden in the celebration, buried in terabytes of data, and in the silent pauses of the scientists who studied it, were whispers of anomalies, subtle irregularities in the brightness of the photon ring, unexpected flickers in flares near the horizon, magnetic fields twisting in ways the equations struggled to explain, jets of plasma, too powerful, emerging with too much order from the chaos. These were not flaws of imagination, nor tricks of instrumentation. They were signatures, faint but persistent, that the event horizon might not be the smooth, silent veil Einstein's equations foretold. Instead, it hinted at something more, an edge alive with secrets, a frontier haunted by questions we had not yet learned to ask. The discovery phase was over. Humanity had stared at the border of reality and confirmed its existence. But what it found was not silence. It was the beginning of whispers, anomalies that suggested the horizon was not an ending, but a doorway into mysteries deeper than science had ever dared to imagine. For nearly a century, the event horizon had been described as an immaculate frontier. It was the ultimate boundary, a surface of silence where no particle, no photon, no whisper of information could ever cross outward. According to Einstein's equations, this horizon should be perfectly featureless. It was not a place of turbulence or activity, but rather the edge of absence itself, the line beyond which the universe ceased to speak. If a black hole was to exist, its horizon would stand as a smooth curtain between the known and the unknowable, a mathematical perfection that offered no surprises. But when astronomers turned their instruments toward these cosmic abysses, they did not find the quiet minimalism that theory promised. Instead, they began to record irregularities, strange pulses, and radiant signatures that seemed to come from the very brink of the event horizon. One of the most unsettling discoveries came from the galactic center. As telescopes monitored Sagittarius, bursts of energy would sometimes erupt near the horizon. These flares, visible in X-ray and infrared bands, were not random explosions. They flickered in ways that seemed structured, almost patterned, as though echoing some hidden rhythm. In 2018, the European Southern Observatory's Very Large Telescope captured what appeared to be a hotspot, a compact region of plasma, orbiting Sagittarius A at a significant fraction of the speed of light. This orbit, so close to the edge, traced the very limits of Einstein's predictions. Yet the precise timing and brightness of the flares did not always match what models had anticipated. It was as though the black hole's edge was not merely swallowing matter, but choreographing it in unexpected ways. Then came the jets. Across galaxies, astronomers have observed thin beams of plasma, sometimes stretching for hundreds of thousands of light years, emerging from the centers of black hole systems. These relativistic jets carry extraordinary power, blasting matter at speeds close to light and shaping the evolution of entire galaxies. Yet their origin remains shrouded in confusion. According to classical relativity, nothing should emerge from within the horizon itself. And yet, these jets seem to be launched from regions perilously close to that invisible edge. Magnetic fields are suspected to play a role, twisted by the black hole's spin and fed by the accretion disk. But the sheer scale and order of these streams of energy defy easy explanation. How can such precision arise at the edge of chaos? How can such luminous power be organized at the boundary where light itself is meant to fail? The contradictions deepened further when quantum physics entered the conversation. In 1974, Stephen Hawking made a prediction that shook the foundations of physics. Black holes, once thought to be eternal, should actually radiate energy. This emission, known as Hawking radiation, arises not from the interior of the black hole, but from the strange quantum processes at its boundary. Virtual particle pairs flicker into existence in the vacuum near the horizon. Normally, these pairs annihilate one another instantly, returning their borrowed energy to the void. But near a horizon, one particle can fall inward, while the other escapes, carrying energy away into space. The black hole, in this exchange, loses mass. Over immense timescales, it evaporates. The idea was revolutionary, for it implied that black holes were not black at all. They glowed faintly with thermal radiation, eventually shrinking to nothing. Yet this prediction stood in stark opposition to Einstein's vision. General relativity had described the horizon as smooth and silent. Hawking's quantum analysis painted it as a site of restless activity, where particles and energy conspired to undo the black hole itself. Two great pillars of physics, relativity and quantum mechanics, collided at this border, leaving behind paradox rather than harmony. Among the strangest consequences of this collision is what has been called the firewall paradox. In the framework of relativity, an astronaut falling through the event horizon would experience nothing unusual. The passage would be seamless, with no sudden wall or burst of radiation. But quantum theory suggests otherwise. To preserve the laws of information, some physicists argue that the horizon must actually burn with unimaginable intensity, creating a wall of searing energy that would annihilate anything attempting to cross. The graceful veil of Einstein becomes, in this view, a furnace of quantum violence. The mere possibility of such a firewall forces physics into a profound crisis. Either relativity is incomplete, or quantum theory fails in ways we do not yet grasp. The event horizon, once considered the most predictable of cosmic boundaries, transforms into a battleground between two world views. The shock for astronomers lies not only in the equations, but in the data itself. Gravitational waves, captured by the LIGO and Virgo observatories, carry whispers from colliding black holes. In these faint tremors of spacetime, scientists search for deviations, echoes or distortions that might reveal the horizon is not as pristine as it seems. While the results remain debated, hints of anomalies linger in the noise, tempting physicists with the possibility that the horizon might echo rather than remain silent. Even the photon rings captured by the Event Horizon Telescope show subtle irregularities. Instead of perfect symmetry, slight distortions appear. Some may be due to the interstellar medium, some to instrumental limits, but others suggest complexities in the way light bends and orbits the edge. If the horizon is alive with turbulence, then perhaps the images are not merely confirming Einstein, but revealing something beyond him. To the scientific community, these contradictions are more than technical puzzles. They represent fractures in the very foundation of understanding. The black hole, once imagined as a silent devourer, now appears restless, paradoxical, and possibly self-contradictory. Plasma jets erupt as though rebelling against the rules. Hotspots circle with impossible precision. Quantum fields threaten to replace smoothness with fire. Hawking's equations foretell an end, even as relativity insists on eternity. The event horizon was supposed to be the simplest surface in the universe. Instead, it has become the most haunted. The shock of these discoveries ripples far beyond the laboratories and observatories. It strikes at philosophy itself. For if the horizon is unstable, if its laws are contradictory, then what does that say about the unity of nature? If physics cannot reconcile its two greatest frameworks at the brink of a black hole, then perhaps the cosmos is hinting that its deepest truths remain hidden. Astronomers and physicists stand before these anomalies, not with triumph but with unease. Each irregularity whispers that the universe is not yet ready to surrender its final secrets. The black hole's edge, once envisioned as a silent curtain, now roars with contradictions, forcing humanity to confront a profound realization. The abyss is not passive. It resists comprehension. It distorts predictions. It challenges the very idea that the universe is a coherent, logical whole. The scientific shock is not simply that anomalies exist. It is that they exist where silence was expected. The event horizon, rather than a clean end, may be the most enigmatic beginning, a frontier where the universe itself refuses to obey, where the laws of nature unravel into paradox, and where human understanding must either evolve or collapse under the weight of mystery. The deeper the eyes of science gazed into the abyss, the stranger the reflections became. What began as faint irregularities soon evolved into a catalogue of patterns too persistent to be dismissed as noise. The event horizon, once imagined as the simplest boundary in the cosmos, revealed itself as a surface etched with mystery. It was no longer enough to celebrate its first images. The task became to interrogate them, to peel back every photon, every flare, every trembling signal carried from the edge of the unknowable. The Event Horizon Telescope, with its Earth-sized lens of synchronized observatories, offered humanity its first glimpse of a black hole's silhouette. But hidden in the raw data were subtleties that resisted easy interpretation. The bright ring of light encircling M87 and Sagittarius A was not a perfect circle of serene symmetry. Certain regions glowed more intensely, creating patches of brightness that shifted across time. Some models explained this as turbulence in the accretion disk, or as the dance of magnetic fields threading through plasma. Yet the irregularity seemed persistent, hinting that the horizon was not a silent edge but a restless frontier. X-ray observatories like Chandra soon added another layer to the puzzle. Sagittarius A, though usually quiet, sometimes erupted with sudden flares of high-energy radiation. These outbursts, lasting only minutes to hours, appeared without clear cause. More unsettling still were the oscillations embedded in the data. The X-ray brightness would rise and fall in rhythmic pulses, as though something near the event horizon were circling in and out of view. These quasi-periodic oscillations were not random bursts of chaos, but patterns, timed and repeated, betraying a structure at the very threshold of spacetime. To scientists, it was as if the black hole's shadow was whispering a rhythm, a cosmic heartbeat too deliberate to ignore. Infrared telescopes extended the view, piercing through the shrouds of dust that veiled the galactic center. They revealed hotspots racing around Sagittarius A at dizzying speeds, orbiting perilously close to the Schwarzschild radius. Some moved faster than expected, completing circuits in mere minutes. Einstein's equations described such orbits as possible, yet the observed precision and brightness of these spots raised questions. Were these simply clumps of plasma, or manifestations of deeper processes encoded into the fabric of the horizon itself? Even light itself, bent by gravity into circles of defiance, seemed to tell a stranger story than expected. General relativity predicted that photons skimming the edge of a black hole would form concentric rings, stacked layers of light orbiting before escaping. Yet in the EHT data, the brightness of these photon rings did not always conform to predictions. Some appeared distorted, others amplified, as though additional forces were shaping them. Perhaps it was turbulence in the accretion disk, perhaps interstellar scattering, but perhaps it was something more, something intrinsic to the horizon's edge. Meanwhile, computer simulations of black hole accretion grew ever more detailed. By feeding the laws of magnetohydrodynamics into powerful algorithms, scientists recreated virtual black holes, complete with swirling disks of plasma and tangled magnetic fields. The simulations revealed chaotic storms, turbulence that shredded order into disorder, and angular momentum transferring in ways that defied expectation. In many cases, the behavior of matter near the horizon differed subtly from theory, producing jets and flares more powerful than the input equations allowed. The horizon, in simulation as in observation, seemed less a passive surface and more an active participant. The jets themselves posed perhaps the most dramatic question of all. Across the universe, supermassive black holes launch collimated streams of plasma that pierce through galaxies like cosmic lighthouses. These jets stretch for hundreds of thousands of light years, carrying energies that dwarf the output of entire stellar populations. Yet their birthplace lies tantalizingly close to the event horizon. How can matter be expelled outward from a region where even light is trapped? Magnetic fields twisted by the spin of the black hole may tap into rotational energy and sling matter outward through mechanisms like the Blanford-Znajek process. But even these models strain under the sheer efficiency of the jets. Observed powers often exceed predictions, leaving unanswered whether hidden physics lies at the heart of these luminous streams. Gradually, a pattern emerged. These anomalies were not isolated curiosities. They repeated across different black holes, in different wavelengths, through different instruments. The irregular brightness of photon rings, the hotspots tracing impossible orbits, the flares flickering in echoing rhythms, the jets launched with mechanical precision from the edge of the abyss. Each observation carried its own uncertainty, but together they formed a chorus of dissonance. The horizon, long thought to be the simplest feature of Einstein's universe, was beginning to look like the most complex. Some physicists began to wonder, were these patterns the fingerprints of new physics, encoded not in distant galaxies, but in the very frontier of nothingness? Could the horizon conceal phenomena that neither relativity nor quantum theory had yet described? If so, then the anomalies were not errors, they were clues. The subtle distortions of light, the rhythmic flares, the impossible jets, all fragments of a larger truth hidden in the veil of gravity. To investigate further, astronomers layered instruments like brushstrokes on a canvas, Chandra in X-rays, the Very Large Telescope in infrared, the EHT in radio waves. Each painted a different dimension of the horizon. By combining these views, they constructed multi-wavelength portraits of black holes in motion. Time-lapse data, revealed correlations. X-ray flares often coincided with infrared bursts, as though multiple messengers were emerging from the same hidden event. The horizon was not silent. It was communicating in codes of radiation, scattering hints of its nature across the spectrum of light. The philosophical implications grew heavier. If the event horizon was meant to be absolute silence, but instead delivered patterns and echoes, then perhaps it was not a boundary at all. Perhaps it was a membrane, a surface with properties still undiscovered, storing or releasing information in ways that defied the old image of a clean one-way veil. For scientists, this raised questions not only of astrophysics, but of ontology itself. Was the horizon a place, a condition, or a deception? An illusion created by incomplete equations? The deeper investigation did not resolve the paradoxes, it deepened them. Every new image, every new simulation, every new burst of radiation added texture to the enigma. The anomalies were not accidents. They repeated with too much persistence, too much pattern, too much rhythm. Like ancient astronomers watching the heavens for omens, modern scientists found themselves staring at data that seemed to whisper of hidden laws buried in the chaos of the abyss. The black hole's edge had once been the final curtain of physics. Now it was becoming the stage upon which the deepest mysteries of existence performed in silence and light. The task was no longer to confirm Einstein's equations. It was to understand what lay beyond them, to listen to the echoes that the universe was not supposed to make. The deeper humanity investigated, the more it became clear. The horizon was not the end. It was the beginning of a question larger than physics had ever asked. Every great scientific mystery has a moment when questions cease to be whispers on the edge of understanding and rise into thunder that cannot be ignored. For the enigma of the event horizon, this escalation came not as a single revelation, but as a chorus of contradictions, each one striking against the bedrock of physics. What was once a silent veil now threatened to unravel the two greatest theories humanity had ever written. Einstein's relativity had painted black holes as inevitable, their horizons smooth and absolute. Yet as telescopes sharpened and instruments listened to the trembling of spacetime itself, the confidence of that vision began to falter. The horizon was no longer behaving as Einstein's mathematics had promised. Subtle deviations crept into the data, tiny cracks in what had once been thought unbreakable. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, captured the first direct detection of gravitational waves, ripples in space-time caused by the violent collision of two black holes. It was a triumph unlike any before it, confirming predictions Einstein himself had doubted would ever be observed. But within these signals lay a puzzle. The gravitational waves did not cease the instant the black holes merged. Instead, the newly formed black hole vibrated, ringing like a struck bell. This phase, known as the ringdown, was expected. General relativity predicted precisely how these oscillations should fade. Yet in some cases, the signals carried faint irregularities, deviations so slight they could be mistaken for noise, but persistent enough to raise unease. Some researchers suggested that these were echoes, subtle repetitions of the gravitational waves, as though the horizon itself reflected a fraction of the energy. If true, it would mean the event horizon was not the silent absorber Einstein envisioned, but a surface with texture, a boundary that could answer back. The possibility of echoes ignited controversy. Many argued the signals were statistical illusions, artifacts of imperfect detectors. But others saw them as the first evidence that the event horizon was not smooth at all, that new physics lurked at its boundary. For if even gravitational waves, the purest messengers of spacetime, could be distorted, then relativity itself was under siege. The escalation did not stop there. Black holes raised questions about the very fate of information, one of the deepest principles of quantum theory. According to Einstein, anything crossing the horizon is lost forever to the external universe, swallowed without return. Yet, quantum mechanics demands that information is never truly destroyed. Every particle, every quantum state, carries imprints that must be preserved, even if scrambled beyond recognition. The horizon, in Einstein's view, annihilates these records. In quantum theory, such destruction is forbidden. This conflict became known as the black hole information paradox. Stephen Hawking first exposed its sharpest edge when he demonstrated that black holes radiate. Over vast timescales, they evaporate into nothing. But if they vanish, what happens to the information of everything they consumed? Does it dissolve into non-existence, or is it preserved in ways we cannot yet see? Hawking himself wrestled with the contradiction, revising his position late in life, but leaving no definitive resolution. The anomalies discovered near horizons seem to intensify this paradox. The quasi-periodic oscillations in flares, the structured hotspots, the distorted photon rings, all might be interpreted as signs that the horizon was not destroying information, but struggling to encode it, to preserve the cosmic ledger that quantum law insists must survive. In this view, the anomalies were not random at all, but desperate signals of physics attempting to reconcile itself. Quantum entanglement added yet another layer of strangeness. When two particles become entangled, their states remain linked no matter how far apart they travel. If one falls into a black hole, what becomes of its partner? Some theories suggest the horizon itself must participate in this entanglement, storing information on its surface in a form still hidden to us. Others argue that entanglement breaks down at the edge, producing the feared firewall, a searing wall of radiation that destroys everything attempting to cross. Both possibilities strike at the core of reality, challenging the unity of space, time, and information. The more scientists probed, the less certain the horizon became. It was no longer a clean, predictable boundary, but the most unstable frontier. In physics, Einstein's equations had described it as inevitable, smooth, and final. Quantum theory described it as restless, violent, and paradoxical. The two visions clashed at the horizon, neither yielding, neither able to claim victory. To imagine the horizon as absolute now seemed naive. Instead, it appeared as a battleground, a liminal space where laws bent under pressure. Gravitational waves hinted at echoes. X-rays pulsed in rhythms too precise for randomness. Photon rings shimmered with irregular brightness. Each anomaly was a fracture line, a sign that the border of the abyss was alive with tensions unresolved. For astronomers, the escalation was sobering. The closer they looked, the more the abyss resisted simplicity. Black holes were once dismissed as mathematical curiosities. Then they became engines of galaxies. Now they threatened to undo the very frameworks that had made them imaginable. They stood not as confirmations of Einstein's brilliance, but as questions so vast they might outlive even his legacy. The event horizon, once described as the cleanest concept in astrophysics, now seemed the most haunted. It absorbed not only matter and light, but also the confidence of science itself, turning clarity into doubt, precision into paradox. Each new anomaly deepened the suspicion that the horizon was not an end, but a mirror, reflecting back humanity's incomplete understanding of reality. In this escalation, the black hole ceased to be a solitary object in the void. It became a stage upon which the greatest drama of physics unfolded. Relativity and quantum mechanics, the twin pillars of modern science, clashed in silence at its edge. The anomalies were not mere curiosities. They were cracks in the edifice of knowledge, inviting the possibility that beyond the horizon lies not only darkness, but a revolution waiting to be born. When the boundaries of knowledge begin to fracture, theories rise like scaffolds over ruins, attempts to hold together what the universe itself threatens to dismantle. The event horizon, once imagined as a clean and final line in space-time, has become the most uncertain edge of physics. It refuses to behave like the obedient frontier Einstein described. Instead, it vibrates with anomalies, pulses with contradictions, and forces scientists to imagine realities stranger than fiction. To confront these mysteries, new theories emerged, not as final answers, but as speculative bridges across the abyss. Each theory paints the horizon not as silence, but as a stage where hidden physics performs in shadows. One of the most unsettling possibilities is known as the firewall hypothesis. In classical relativity, nothing unusual occurs at the horizon. A falling astronaut would notice no sudden change, only a gradual journey into darkness. Yet quantum mechanics demands otherwise. To preserve the sanctity of information, the horizon may ignite into a wall of unimaginable radiation, a searing barrier that incinerates anything daring to cross. This so-called firewall would rewrite the serenity of Einstein's vision into violence, making the horizon a cosmic furnace. Though unproven, the hypothesis lingers as a ghost in the data, an idea too terrifying to dismiss, too radical to accept without proof. Other physicists seek resolution not in destruction, but in deeper structure. Fuzzball theory, born from the mathematics of string theory, imagines that black holes are not voids at all, but tangled conglomerates of vibrating strings. In this view, the event horizon does not exist as a smooth surface. Instead, what appears as a horizon is the woven edge of countless microstates, filaments of energy wrapped into cosmic knots. The anomalies, the unexpected flares, the uneven photon rings might then be glimpses of this hidden texture, hints that the black hole is not a featureless abyss, but a storm of quantum threads. Still, the quest for answers has carried some physicists into even more daring terrain. Juan Maldacena and Leonard Susskind proposed a radical idea, EREPR, a conjecture suggesting that entangled particles and wormholes may be two faces of the same phenomenon. If true, the horizon of a black hole could be threaded with invisible tunnels of spacetime, quantum bridges linking distant regions of the cosmos. The event horizon might then be more than a boundary. It could be a gate, its anomalies not signs of chaos, but whispers of hidden connectivity. In this vision, black holes are not tombs, but bridges, binding the fabric of the universe in ways both wondrous and unnerving. Other proposals are subtler, rooted in the belief that information must leave faint imprints. The idea of quantum hair suggests that black holes are not entirely bald, as classical relativity demanded. Instead, they may carry delicate fluctuations at their horizons, tiny variations in quantum fields, encoding the identities of the matter they consumed. These fluctuations would be nearly invisible, yet enough to preserve information, allowing the universe to keep its books balanced. What looks like smooth darkness from afar may in fact be an intricate skin of memory, a record written in trembling, quanta. But perhaps the boldest of all is the holographic principle. Gerard Hooft and Leonard Susskind imagined that the three-dimensional reality within a black hole may not be real at all. Instead, everything inside could be encoded on the two-dimensional surface of its horizon, like a hologram storing the illusion of depth. If this principle is true, then the anomalies are not imperfections. They are windows into the deepest architecture of reality, a reminder that the universe itself may be a grand hologram. Black holes, in this light, are not just objects, but projectors of cosmic truth, surfaces where dimensions collapse into code. And yet, the horizon's puzzles have inspired even stranger possibilities. Some physicists have wondered whether black holes are not black holes at all, but mimickers, objects like gravastars or boson stars, exotic structures formed by new physics. These entities could produce shadows and flares similar to black holes but without true horizons. If such imposters exist, then the very images captured by the Event Horizon Telescope may not be what they seem, but illusions sculpted by unfamiliar matter. In this unsettling scenario, humanity may have mistaken a shadow for something else entirely. Each theory, from firewalls to holograms, from fuzzballs to quantum hair, carries a common message. The horizon is not simple. It is layered, encoded, textured, haunted by laws not yet written. For some, these ideas feel like glimpses of a greater theory of quantum gravity, the elusive unification of Einstein's geometry with the probabilities of the quantum world. For others, they remain fragile scaffolds, destined to collapse under the weight of further observation. What binds them all is the recognition that the event horizon cannot be dismissed as empty space. It is not the clean, silent veil of old textbooks, but the most enigmatic stage in the universe, a stage where paradox performs. Its anomalies are not mistakes, they are signals. Each flare, each distortion, each gravitational echo may be the universe's way of telling us that something deeper lies beneath. And in this haunting chorus of speculation, the horizon becomes more than a place. It becomes a mirror, reflecting the uncertainty of science itself. Every theory is a reflection of human longing to understand. Every paradox, a reminder that knowledge is fragile. At the edge of a black hole, reality seems to tremble, daring humanity to look closer, to question deeper, to wonder whether the abyss is not an end, but a beginning. The speculation continues, each idea stranger than the last, each one bringing humanity closer to the truth or farther into illusion. No theory yet holds the final word. The horizon waits in silence, indifferent to human imagination, its secrets locked in shadows. But the deeper science looks, the more the abyss answers. Not with clarity, but with mystery. When nature conceals its secrets, humanity turns to its instruments, building machines that are themselves acts of faith. To look beyond the veil of the event horizon, to test whether the anomalies are illusions or the first cracks in physics, scientists have fashioned eyes that see the invisible and ears that listen to the vibrations of space-time itself. Every telescope, every detector, every simulation is an extension of human curiosity, reaching toward a frontier that does not wish to be seen. The Event Horizon Telescope was only the beginning. A network of radio observatories spanning the Earth, it stitched together our planet into a single colossal lens, capable of resolving the silhouette of a black hole for the first time. Its triumphs, the images of M87Con in 2019 and Sagittarius A in 2022, were hailed as the ultimate confirmation of Einstein's vision. Yet, buried in its streams of data, scientists found subtle irregularities. Photon rings brighter than expected, flickers of structure where only smooth darkness should exist. To confront these puzzles, the telescope is being expanded. New stations, higher frequencies, and sharper resolutions are planned, promising to transform the fuzzy shadows into sharper portraits. The hope is that, with greater clarity, the truth will emerge, whether the horizon is the clean edge of relativity or something far stranger. But vision alone is not enough. The cosmos also speaks through gravitational waves, ripples in space-time, unleashed by black holes colliding. Instruments like LIGO and Virgo have already recorded dozens of these cosmic cataclysms, each one a symphony of warped space-time. In CEM, their final notes, the so-called ring-down phase, lie subtle deviations, tiny echoes that should not exist if horizons are smooth. To probe deeper, humanity looks to the future. The Laser Interferometer Space Antenna, LISA, a triangular constellation of spacecraft stretched across millions of kilometers, drifting through the silence of interplanetary space. Alongside it, the Cosmic Explorer, a detector on Earth 100 times more sensitive than today's observatories. These machines are designed not just to hear black hole mergers, but to discern whispers within the echoes, signals that could reveal whether horizons shimmer, fracture, or conceal hidden layers of physics. Meanwhile, other instruments turn their gaze to the light black holes cannot fully hide. The James Webb Space Telescope, suspended in the cold void beyond the Moon's orbit, brings infrared eyes capable of tracing the glow of gas as it spirals toward annihilation. Webb can peer through dust that blinds other observatories, mapping the turbulent neighborhoods of black holes with exquisite precision. Already, its images reveal filaments of gas feeding supermassive giants at the hearts of galaxies, luminous streams that bend and twist under immense gravity. Yet here too, discrepancies emerge, patterns of heat and motion more complex than models predict, as if the very act of falling into darkness writes a new script for matter and light. Beyond the infrared lies another frontier, the domain of X-rays, where matter screams as it nears the abyss. Missions like XPE, the Imaging X-ray Polarimetry Explorer, measure not just the brightness of these rays, but their polarization, the subtle orientations of their electric fields. Through these patterns, scientists glimpse the magnetic structures near horizons, twisted fields that may be responsible for launching jets of plasma across thousands of light years. The anomalies, jets carrying more power than theory allows, hotspots whirling faster than relativity predicts, may find their explanation in these magnetic skeletons, or they may only deepen the mystery, revealing structures that no existing model has yet captured. Yet telescopes and detectors are not enough. The horizon is too distant, its truth too elusive. And so, scientists build the cosmos inside machines. Using the mathematics of general relativistic magnetohydrodynamics, they simulate black holes on supercomputers, weaving together equations of gravity, plasma, and light. These digital experiments recreate accretion disks, magnetic fields, and jets, allowing researchers to compare simulated skies with real observations. In these simulations, anomalies sometimes arise, unexpected turbulence, unexplained instabilities that mirror what telescopes record. Each time, scientists are left to wonder, are these errors in the code, or hints that the code of physics itself is incomplete? But perhaps the boldest frontier does not lie in space or in equations, but in the laboratory. Physicists have begun to create analog black holes using superfluids, laser-driven plasmas, and carefully engineered quantum systems. These constructs do not bend spacetime, but they mimic the mathematics of horizons, creating artificial boundaries where waves cannot escape. In these miniature universes, researchers have glimpsed behaviors reminiscent of Hawking radiation, tiny quanta escaping where none should. If horizons can be imitated in the lab, perhaps their secrets can be coaxed into the open, their mysteries reduced to measurable patterns. These analogues may never capture the full violence of a true black hole, but they offer something almost as precious: the possibility of testing, repeating, and refining our theories under controlled conditions. Each of these tools, telescopes, detectors, simulations, laboratories, is a different sense organ for humanity, each one straining to hear the whisper of the horizon. Together, they form an orchestra of inquiry, probing light, sound, magnetism, and mathematics. Yet with every advance, the mystery deepens. Sharper images reveal more irregularities, more deviations. Gravitational wave echoes suggest subtle cracks. Simulations struggle to reconcile turbulence with order. Laboratory horizons whisper quantum truths, but never the full story. The event horizon remains a veil, not absolute, but translucent, revealing only fragments. Are the anomalies mere artifacts of measurement, errors born of imperfect machines? Or are they signals pointing to physics unimagined? The difference is profound. If they are illusions, the horizon is what Einstein predicted, a smooth boundary that confirms relativity. But if they are real, then every instrument, every experiment is not just observation, it is excavation, peeling back the layers of a deeper truth. What science seeks now is not a single image or a single signal, but a convergence. If the Event Horizon Telescope sees irregular photon rings, if Webb maps heat flows that contradict models, if gravitational detectors hear echoes, and if simulations reproduce the same anomalies, then the case grows undeniable. The horizon will no longer be myth or metaphor. It will be revealed as something beyond the textbooks, beyond Einstein, beyond the boundaries of our imagination. For now, the effort continues. Each new instrument is a hand extended into darkness, each dataset another fragment of a cosmic puzzle. The horizon resists, concealing its truths in silence. But humanity does not relent. With every advance, the veil thins, and somewhere in those shadows, the answer waits. Whether the anomalies are mirages, or the first glimmers of a revolution in physics. At the edge of a black hole lies not just a boundary in physics, but a boundary in thought. The event horizon is both an astrophysical surface and a metaphorical abyss, a mirror where science and philosophy converge. For a century, it has been imagined as the ultimate edge of reality, the point where all journeys end, where time and space themselves fall silent. But the anomalies whisper otherwise. They suggest that even here, at the supposed final frontier, the universe still writes, still invents, still conceals. The horizon is not closure. It is a question that refuses to resolve. Humanity has always lived with horizons. In ancient times, it feared the edge of the earth, believing oceans poured into voids. To sail too far was to vanish into nothingness. Yet those horizons dissolved, replaced by continents, skies, and new worlds. Today, the event horizon of a black hole has become the new abyss, the place where certainty falters, where fear takes root. It is no longer the map's edge, but the universe's edge, and humanity stares into it with the same mixture of dread and longing. If the anomalies are true, then horizons are not absolute. They are shifting, layered, and alive. The cosmos may not be a finished manuscript, but a living draft still being written in light and gravity, in quantum whispers and gravitational waves. Each flare near Sagittarius A, each gravitational echo in LIGO's detectors, each distorted photon ring in the Event Horizon Telescope's data is a footnote from the universe itself, a reminder that what we call truth is only provisional, a fragile scaffolding built over mysteries that extend deeper than imagination. And in this cosmic theater, black holes mirror humanity's most intimate fears. Just as horizons consume stars and erase histories, human beings face their own horizons: mortality, time, finality. Death is the personal event horizon, the place beyond which nothing returns. Like astronomers peering into shadows for signs of anomalies, humanity searches for meaning in its own darkness, hoping that finality is not truly final. Perhaps this is why black holes haunt the collective imagination, not simply because they are powerful, but because they reflect the deepest uncertainties of existence. The firewall paradox, the holographic principle, the whispers of quantum hair, these are not merely scientific puzzles. They are philosophical tremors shaking the foundations of what it means to exist. If a black hole can store memory on its surface, then perhaps nothing in the universe is ever truly lost. If horizons can shimmer with echoes, perhaps death itself is not silence, but transformation. The boundary between physics and philosophy blurs, as it so often does at the edges of knowledge. The anomalies leave astronomers restless. They comb through data not only for answers, but because the questions themselves are unbearable to leave unresolved. The irregular photon rings, the unexplained jets, the faint gravitational echoes, these are not mere glitches. They are invitations, daring humanity to look deeper, to question the absolutes it once trusted. Einstein's equations still stand like monuments, but even monuments can crack. Behind the cracks, something more profound waits to be seen. Perhaps the ultimate lesson of the event horizon is humility. To confront the most powerful objects in the universe is to realize how fragile knowledge is. Each breakthrough, whether it be the image of M87 HAG, the detection of a merger by LIGO, or the delicate polarization patterns in X-rays, is not an answer, but a doorway. With every doorway opened, more corridors appear. The closer humanity comes to the abyss, the less certain the ground feels beneath its feet. And yet, there is wonder in this uncertainty. For if the universe were closed, if the laws of physics were finished, discovery would end. Instead, the anomalies remind us that reality itself may be an unfinished poem, a song still being composed by forces beyond comprehension. To live in such a universe is to live in perpetual awe. In the end, the event horizon is not just a place in space. It is an idea. It is the frontier where science collides with mystery, where human curiosity confronts the infinite. Astronomers are haunted not only by what their instruments record, but by what those signals imply. That existence itself may be more fragile, more wondrous, and more mysterious than ever imagined. The horizon remains silent, yet it speaks through echoes and light, through whispers of data carried across billions of years. Its anomalies may be errors, or they may be truths that change everything. Humanity cannot yet know, but the pursuit itself, the act of listening to shadows, is its own form of meaning. And so, the story does not end at the event horizon. It begins there. It begins with every unanswered question, with every flare that defies theory, with every echo that refuses silence. The horizon is not finality. It is invitation, a reminder that the universe, like life itself, is not a closed book but an unfolding manuscript, each page revealed only as we dare to turn it. The last word belongs to the cosmos, and it has not yet been spoken.